Hi, everyone. Thanks for joining me here today. My name is Sri, and today I'll be walking you through a journey that I had building a music recognition app that can identify songs by singing or humming. And so I want to just share some learnings that I had while building this sort of experimental demo. And hopefully today you'll walk away with more insights on audio embeddings, what those are, and embedding models for audio and some of those applications for those embedding models, as well as a really cool Spotify ML model and DataStax' database, AstroDB. And so before we hop in anything, I just want to quickly introduce myself. So my name is Sri. I'm based out of San Jose. Even though I'm literally 50 miles away, every time I come to SF, I freeze here for some reason. But I'm also a former developer relations intern at DataStax. And so DataStax is a really awesome company. They build tools and products for developers to build Gen AI apps. And so definitely check out some of their tools. And over the summer, I had a really amazing experience getting to kind of explore a lot of the AI space. I went to a lot of events like these, conferences, and learned a lot about different tools that were out there. And so that was super exciting. I'm also a current senior studying computer science at Cal Poly, and I'm a nature lover and a music nerd. I love listening to music, different types of music, going to live events, and I've also played guitar and drums here and there. And so when over summer, when I was given this sort of task of building out a demo app, I kind of thought to myself of this issue that I think all of us have faced at some point, where you have a song or melody that's stuck in your head, and the only thing that's coming to mind is this tune. There's no words, you don't know the artist. And current solutions out there like Shazam or SoundHound, they use this technique called audio fingerprinting, which is basically intensive noise filtering to do an exact audio match. If you tried humming into Shazam, that's not going to work. And so that's kind of the inspiration for this app. I wanted to create this proof of concept of app you can hum into. And if any of you guys are looking for a startup idea, please, nothing is out there that kind of solves this issue. And so Google engineers, though, they work to kind of integrate this into their search engine. And the tool mostly works for kind of popular songs at the moment. If you were to try it on something a little more rare, it's kind of fumbles. But this is the idea. And so to start off, I had to think about how I wanted to match hummed audios to recorded audios. And I needed to kind of standardize both formats into a data type that would represent like the key features of the music, like pitch, timbre, the spatial characteristics. And this is where audio vector embeddings play a perfect role. And so what are audio vector embeddings? They are basically numerical arrays that represent important sound features. You start off with an audio file, and that gets converted into a visual spectrum of frequencies called a spectrogram. This is fed into a deep neural network, which outputs a learned representation of our audio. And so when you have these vectors, these points in space that sort of represent audios, you can utilize vector similarity search to kind of identify similar songs that are in space together. So I was kind of taking this idea and thinking that if I had a hummed audio and a recorded audio, they would be close in space together. And so my first kind of approach was to use some pre-trained embedding models, or at least explore if there were pre-trained embedding models out there. And I found that there were some really cool open source Python libraries called PANS Inference, OpenL3, and I also looked into VGGish and Wave2Vec. Definitely some really great models out there that I would totally recommend exploring. But I want to focus in on PANS and OpenL3. So PANS stands for Pre-Trained Audio Neural Networks. It's basically this collection of deep learning models designed for audio-related tasks that are trained on expansive audio datasets. And PANS Inference specifically specializes in audio tagging, which I didn't understand until I tried to use it for this task. But audio tagging is kind of the idea of putting text and metadata onto audios. So like if I had a really sad and somber audio, it would add the words sad, somber, and like tag that onto the audio to just sort of describe it. And so this didn't work too well for the use case of matching hummed audios to recorded audios. But I want to hop over onto AstroDB right now where I have this database loaded with records with basically vector data that was produced by PANS Inference. So I have a bunch of data here. It's tracks, artists, album, date, all that. And I'm going to perform vector search within the database on some of these songs so we can kind of look at the results. So let's do Young and Beautiful, Lana Del Rey. It's kind of a slower, sad song, sort of dramatic. And if we look at some of these similar results popping up at the top here, a lot of them have the same sort of energy to them and the same sort of musical quality. They're very similar, like sad songs in a way, or maybe not sad, but like dramatic and have similar sort of tone to them. Let's try another one. Let's do Sicko Mode, Travis Scott. We see now a lot more like rap songs are showing up, more like upbeat hip hop songs. And then if I were to do, let's do Everlong, Foo Fighters, one more. Now we're seeing some more like grungier, like rock songs, And so these results were super interesting. I think that PANS Inference and this embedding model has a really awesome application for music recommendation systems based on the actual intrinsic quality of the music, It also do really maybe even sentiment analysis, being able to identify like upbeat songs with upbeat songs and more like somber songs with somber songs. And so continuing on. Another cool embedding model that I was looking into was OpenL3. This model is basically based off of this L3 architecture, and it does joint audio and visual learning on video data. And so this could be super useful for some of the use cases listed here, like audio-visual matching, scene understanding, multimodal sentiment analysis. But when I tried to work with this embedding model, it was pretty slow with its embedding generation. And so for an app that I just wanted to kind of like pull up and sing into and have it quickly output the song I'm singing, I needed something that would be a little bit quicker with the embedding generation. And so after kind of having not some great success with working with pre-trained embedding models, I kind of thought to myself, like, what is in a hum or in like a song? It's kind of just the audio, it's just the melody of it. And so maybe we didn't need something that was this like such learned representations. Maybe we needed something a little more simple. And so I started doing a little more research on these like query by humming models. And a lot of them interestingly talked about using MIDI data to represent audio. And so MIDI stands for Musical Instrument Digital Interface. It is basically a set of numbers that represent the digital audio of music. It's kind of similar to how like ASCII represents text. And it conveys detailed musical instructions with these musical events, basically described with the integers of event type, the key on the musical keyboard pressed, like middle C is 60, C sharp is 61, and so forth, and the note loudness. And so how can we now use this idea of MIDI data to create audio embeddings? Well, if you remember those musical events, the keyboard notes seems like a perfect way of representing melodies. If you take a recorded audio, turn it into keyboard notes, take a hummed audio, turn it into keyboard notes, those sort of have the same kind of sound in a way. And there are many algorithms that are out there for doing this audio to MIDI translation, but I really enjoyed working with Spotify's Basic Pitch. It's a open source library. They have a TypeScript library, a Python library out there. And they do amazing note prediction and MIDI output generation, as well as real-time processing, which kind of gets all of the sort of things that I wanted for creating this application. So I'll kind of show you how Basic Pitch works they have this really great interface so you can actually visualize what the ML model is doing. And so I'm going to play a hum. You're going to hear a lot of my singing today, so I apologize for that. But this is a hummed audio of, I believe, Blank Space, Taylor Swift. Okay, that's all. And we're going to do... Thank you. We're going to now look at how this sounds. This is the piano notes of it. It's just the piano notes of that. And so now if I were to go ahead and get actually Taylor Swift, not my voice, this is her vocals isolated to kind of get a better sort of output from this MIDI generation. I'm
insane, 'cause you know I love the players and you.
Yep. And when we have that process, it sounds pretty similar, honestly, to the hummed audio. It's kind of the same piano notes. Yeah. And right here, they have these certain parameters that kind of help with forming better, basically, note predictions. And so now with this information, we can basically try forming our embedding model. And so I'm going to hop over to VS Code over here and show you this function that I created for basically doing this embedding generation. And so right here in my repository for the app that I'm going to show you very soon, it's a pretty simple repository. It's built with the Flask backend, React front end, and I'll walk you through some of these functions and what they're doing. And so we have this function get embeds, basically taking some of the functions from basic pitch, such as their predict and their model output to notes. And basically, these are all those parameters that we saw there on the UI. And it's returning a MIDI data format. From here, we're getting the pitch vector. This is basically getting those piano notes from that MIDI output and appending it onto an array. From there, we're taking these piano notes and we're going to normalize them on a scale from 0 to 1 so that we can start doing vector cosine comparisons. And then finally, we are creating a histogram of these notes. And so the order of the notes doesn't matter. It's just kind of looking at the occurrences of them, like how many times is C sharp showing up in this audio. And after that, we're putting it all together and generating an embedding. It's definitely a simplified process, but this was sort of a kind of an experimental look and seeing if this can actually accurately do this sort of hum to search process. And so with this, we can now start loading data into our database. I took a sample of songs here. Basically, this is a sample from a Kaggle database of top 10,000 Spotify songs. And in this function, load data, we are parsing through some of that CSV data. Over here, we're taking that track preview URL. You know how like when you send a Spotify song to someone, you can kind of play it within an app and listen to a track preview. We're taking that because it's sort of the idea is that it encompasses the most important features of the track. And we're writing a URL or writing an MP3 file of that. And then doing that vocal removing part to sort of kind of isolate the vocals and the audio of that. And so this might not be the best for if you're trying to hum a classical song or something like that. But it's doing that sort of for songs that are kind of sung out. It's generating that embedding, and we're using this collections.insert1 function to insert into our database in AstroDB. And so with these two functions, we can start actually testing out our application. So I have this quick file right here called test that just generates an embedding and copies it. And so I'm going to go ahead and run that so we can see kind of what this embedding looks like. So it might take a second because I don't think I ran this beforehand. But in the meantime, let's listen to the audio that we are processing. It's going to be another hum.
Na 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 na. Na, 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 na.
Try to think to yourself if you know what song that is. Let's see. All right. So that now has our embedding copy. I'm going to play this song one more time because it took a second. But
na, 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 na. Na, 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 na.
All right. And so now we're going to go to our database, and I have this collection called songs data now with my data basically generated, the embeddings generated from my generate embedding function. So I'm going to paste this and perform a vector search in the app. And this is the first match that we are seeing over here. Let's go ahead and take a look at what this song sounds like for those who might not know. Let's see.
I tried so hard and got so far, but in the end, it doesn't.
And so that's pretty cool. It actually sounds like what I hummed, and it matched that song just by using these numbers, these sort of array of pitches. And so with that, we can now put a UI on the app. And so I'm going to go back and start up my application. So let's see here. So we can start up the backend by just saying Flask run. And I'll start it by my front end by saying npm run start. All right, so this is a simple UI that I created for the functionality of this app. It basically is taking the songs in the database and displaying them. It has a recording function and also a random hum function to kind of just showcase the style of the app. And so I'm kind of going to go over some of how the functions or the functionality of it works. In here, there's a server file, the backend server, that is basically doing the outputting all those songs from the database, just grabbing in, throwing it on there. And then when the button is clicked to basically find a song, it is doing that process of basically converting it to a MP3 audio and running this function collections.find to be able to perform that vector search and get our results from the database. And so it's pretty cool that we don't actually have to do any of the complex search functionality. It's kind of just calling the database and calling the functions that are within there. Then from there, there's a web recorder JavaScript file that basically is setting up a media recorder and sending over that file when we press the button. And so it's doing that. So let's go ahead and see if this app works. I'm going to start by seeing if it does like music recognition, so let's say I'm hearing this song in like a coffee shop or something. Let's see if it does that. Oh, that's pretty cool. And so now let's try one of the random hums that we have over here. See what that's going to be like. So let's search that. Okay, we're getting this. Pretty cool. It's actually getting some of that in. And so I'll finally also try now a recorded hum that I have, because I think if I sing, it's going to be really shaky. But let's try this and see if this works. And so within our app, we can also maybe hear this. All right, this is still playing on here. All right, let's try that and see if that works. Okay, cool. All right, and so this is basically the app. And this was the product of basically all that research and figuring out these various techniques. And so, yeah, thank you guys so much. And so kind of in summary, we discussed this problem space, having the song stuck in your head, trying to figure out like what you can use to learn this song, figure out what song this is. We learned about audio embedding models and their various applications. Learned about the advantages of MIDI data. And not only is it super compact numerical format data, but it's also really great at conveying musical information. You dove into creating audio vector embeddings with that generate embedding function, utilize vector search to find a solution, and applied all of this in a real world app. And so if you want to learn more, please check out these resources. I have a blog post kind of detailing how I built this app. There's the GitHub repo that's linked up on there, as well as a lot of other information on AstroDB, which was the database that I used for all of the major functionality for this. So thank you guys so much. I'd love to take any questions. The database has only 20 records. That's a really good question because basically this is definitely like a very experimental demo. I think when we saw how the embedding generation function looked, it takes in only like it's a very small function, you know, and so it's not taking into account pitch correction, key correction, time like differences if I started at the very end of the song versus the start. There's definitely like a lot of things that need to be added onto this for it to be a fully functional tool that can be used on like many things. But for the sake of kind of testing it out, yeah, I added about 20 songs. Vectors are basically 128 dimension vectors. I kind of chose that number because I read the Google's Hump to Search blog and they use 128, and so I was like, okay, that's a great number. But also it seemed that most of the tones within a MIDI data were between the numbers of 0 to 127, and so when we're kind of singing like a hum or a pitch, most of the range of like a song is only going to fall between a certain range of numbers, like maybe like 60 to 80. And so in that vector, you're only going to really see the field 60 to 80 populated since it's representing these these pitches. Basically, you're not going to hear a very low note that's represented in the embedding. And so that's why you're going to see maybe like just a couple. But if we were to print out a embedding of like a very long song, it's going to be filled because there's more ranges of notes. On the frequency of, or by range, I mean kind of like pitch range, because our audio is basically, it's keyboard notes, it's pitches. And so it's only taking in the occurrences of certain pitches the most, you know. It's really bad with relative pitch. I actually feel like I became a really good singer doing this project because I had to sing pretty precisely to how this original song was to be able to get the match. And when some of my coworkers at Deus Ex were testing it out, most of them had like deeper voices, and so they would always get matched to this Luke Combs song, no matter what they were singing, and so, or to more male voices. And so, yeah, it doesn't take into account that pitch correction. And I was trying to find ways to do that kind of like key standardization, and I wasn't really able to figure out anything that was working accurately enough in the time that I had. As for vocal remover, I was originally using this algorithm called Demux, but before this presentation, that kind of stopped working for some reason. So I found this GitHub repo and basically just added it to my file and was calling some of the functions from there, and it worked amazingly. And so, yeah.